Hi, my project is Markov chains with an application to Markov chain Monte Carlo. What is a Markov chain? A Markov chain is a stochastic model where the future outcome given the current state is independent of the past. Considering a person walking randomly downtown Montreal, to predict the next street the person moves into, we only need to know where the person is currently at, and the history of the person's position is irrelevant. The main goal of the project is to understand the basic mechanism of Markov chain Monte Carlo by studying the long-term property of discrete time Markov chain. The essential property of a Markov chain is the future given the present is independent of the past. And the necessary property to compute Markov chain Monte Carlo are time homogeneity, the Markov matrix, n-step transition matrix, limiting distribution, stationary distribution, and lastly and most importantly, ergodic Markov chains. To begin, time homogeneity means the probability of event does not depend on time, but only depends on what happened before. Because of the fact that the probability of the event only depends on events happened previously but not the time when the event happened, we can create a Markov matrix showing the probability of all future outcomes given the current state. For example, for a coin flip problem where there is 0.51 chance that the coin comes up as started, we condition on different started sides, tail, and heads, and that's how the matrix will. Furthermore, the Markov matrix we just used only allows us to calculate the probability of an event of the immediate future. To calculate the probability of an event after a longer period of time, we must use the n-step transition matrix. To create such a matrix, we simply take the original Markov matrix to the power of n, and the entries in the new matrix will become the probability of reaching a state after n time interval conditioned on the current state. After introducing the n-step transition matrix, let's talk about the probability distribution of a Markov chain. Given an initial distribution, the probability distribution of the chain is the dot product of the initial distribution and the n-step transition matrix. If after a large number of steps the distribution converges to be the same for every row, the chain has reached its distribution. If we assign the limiting distribution of a chain as its initial distribution, the chain will stay the same from the beginning. If the dot product of the distribution row vector and the transition matrix is equal to the distribution, then the distribution is the stationary distribution. Note that limiting distributions are stationary distributions, but the opposite may not always be true. That is why we have to introduce ergodic Markov chains. They are important because for ergodic Markov chains there exists a unique positive stationary distribution that is also the limiting distribution of the chain. So that means the stationary or the limiting distribution of an ergodic Markov chain is always its stationary distribution. So what is an ergodic Markov chain? It is a Markov chain that is irreducible and aperiodic, and irreducibility means all states are connected either directly to each other or through transition states, and aperiodic means the chain does not have a pattern of the step taken to return to a state after some transition steps. For example, if the chain can return to a state in 1, 2, 3, 7, 8, 9, 10, 23 steps, and we cannot see a pattern, it is aperiodic. And if the states in a chain always return in a pattern such as 2, 4, 6, 8, we can say the chain has a period of 2, then that is periodic. So now we finished talking about certain properties of a Markov chain. Let's jump straight to an example. So given such a matrix on the wrist of forest fire in Ontario, we have to check if it is an ergodic Markov chain, and also find its limiting and stationary distribution. So the chain here is irreducible because all the states are connected with each other directly, like from any state you can go to all the other state. And it is also periodic because for a state such as low risk in any, you can return back to the low risk state in any steps. Thus, we can conclude the chain is an ergodic Markov chain, and this means the limiting distribution of this chain is the stationary distribution of the chain. So how do we calculate the limiting and the stationary distribution of such chain? So you take the matrix to a large power. In this case, at n equal to 17, the chain converges to its limiting distribution, where you see every row is the same. And since this is ergodic Markov chain, the limiting distribution and stationary distribution are the same, so the limiting and stationary distribution is the row vector here. So after finishing talking about the ergodic Markov chain and the other properties of a Markov chain, we can introduce a Markov chain Monte Carlo. Markov chain Monte Carlo is a methodology to use a Markov chain to sample from a distribution. The Metropolis-Hastings algorithm constructs an ergodic Markov chain which has a limiting distribution that is also its stationary distribution. The limiting distribution equals stationary distribution property means that we can run the chain for a long period of time to get the desired stationary distribution we want to sample from. Here is an example of where we have to construct an ergodic Markov chain and run it for a large number of trials. So here we have to construct an ergodic Markov chain using Metropolis-Hastings algorithm to simulate the sampling of from a gamma distribution. So here are some more in-depth mechanisms of how to set up the Metropolis-Hastings algorithm, but the basic idea is that we pick a starting value and a proposal density, we let the algorithm sample from our proposal density and use the acceptance function to accept and reject the proposed value. We do the same process for a large number of trials, such as 10,000 times. Then we can check if our chain reaches stationary distribution if it fits the form of the desired distribution. And for this example, we choose a reflected normal such as this, and the acceptance, since this is a symmetric proposal density, the acceptance which it means that Q of xz and equals Q of zx, which makes the acceptance function becomes this, and it's much simpler to calculate. And implementing all that into programming, it looks something like this. And for n here means number of trial, and sigma, which is the standard deviation you can pick. And for different standard deviation, you might get different distributions that may or may not fit the target distribution you want to sample from. But if you just give different tries, such as like this, I try standard deviation of 1, 0.1, and 2, and we find out that with standard deviation of 1 and 2, my simulated ergodic Markov chain fit the target distribution. And once we know our simulation fits the target distribution, since we know the distribution that constructed the Markov chain, we can sample from our simulated distribution to mimic the sampling from the gamma distribution. And the conclusion is, if we know the form of a distribution but do not know how to sample from it, the Metropolis-Hastings algorithm used the accept-reject sampling method to sample an unknown distribution from a known distribution. And the mixing of this algorithm to the target distribution is largely affected by the starting value and the proposal value you picked.